Swayam Prabha. Digital India. Educated India.
Now, let us improve the model. Let us add one more thing. Suppose there is a constant birth rate within the system, not constant, what I meant is there is a birth rate to the system, but it is not influenced by the carrying capacity. Birth rate is affected by the fractional death rate, and death rate is not influenced by the carrying capacity at all. What will be expected behavior of system? Plot the expected rate level graph, and how can we expect fractional rates to change with the population / capacity ratio. So, just keep this graph in mind, keep this diagram. So, again the left half is exactly the same, only thing now is population is also decreasing at a proportional rate as per the fractional death rate in addition to the net birth rate. Improve model, include including the death rate, is nothing but the fractional death rate D into the population P. So, let us do that. So, that is changing in proportion. What can we expect our behavioral system to be? Will continue to be a shape. In the first case, we reached the carrying capacity C. This point became equal to carrying capacity. Okay. Just to recall. So, looking at one graph like this, one like this, and one for the rate level. Let's start drawing that. Fractional rates. Then I have a population divided by over time. Then I have rates over level graphs. So, the population will continue to exhibit a S-shaped growth, but because there is a see, when you study system composition, what happened? When there is a constant outflow, what happened? We stopped below or above the goal, right? When there is a constant exogenous factor, then we are not able to reach the goal. We either saturate lower or higher depending on direction, whether it is exogenous inflow or outflow. Similarly, when we have a proportional outflow is proportional to the total stock, but the proportionality is constant. Hence, we will continue to exhibit S shape, but we will be stopping below the goal. We will not be able to achieve the same carrying capacity. So, here probably the carrying capacity is here much higher than where we might be able to stop. We will see why that is in a minute. So, let me just for convenience call this as a level. This is a level chart. So, as the level is large, what happens to the death rate? As level increases, death rate keeps increasing, right? It is a constant proportion, right? So, this is a death rate. But birth rate was exhibiting a hump shaped behavior, right? So, let us model birth rate. Birth rate was exhibiting a exponential, not hump shaped graph previously. So, we will continue to have the same graph, but as I draw the hump shape, it will intersect the death rate at some point, correct. So, that means at that point it has to be 0, because when system attains equilibrium, birth rate has to be equal to the death rate. Earlier, when it attained equilibrium, when the birth rate, net birth rate became 0, but here it will attain equilibrium when birth rate is equal to the death rate, right. That happens at this point. So, we can actually plot, that is birth rate minus death rate, as a kind of net rate graph. At this point now becomes a stable equilibrium point. This is an unstable equilibrium point, that is point 0, and your point of inflection is now not net graph, it is called net rate, sorry. And this point now is the peak of the net rate, where it achieves, that represents the point at which that will be the point of inflection. That need not be same as the point at which birth rate peaks. Net rate can peak at a different point than the peak of birth rate. Okay. This is expected behavior. We can continue to visualize it here. Fractional rate, this is P by C, this is large, this is 1. So, your depth is constant D, so nothing changes. In a similar fashion, if you are going to draw the curve, probably we are having looking at a birth rate which is constant, and then we wanted the birth rate to kind of reduce and then come to this point. So, if you assume that as the B, then the net rate, this minus this, probably net rate is somewhere here, and at this point it starts to reduce and intersect somewhere. So, this becomes your net rate, let us not call it rate, net fraction. So, let us incorporate this in a system, in a simulation model, and see how does that look like. So, let us simulate the deaths, incorporate deaths in your SFD model. Fractional death rate D is 0.07, death rate is D into P. Once we do that, we will simulate the SFD model, we'll look at what patterns of behavior observed, what is the stable population size, when does population reach stability, and when is the inflection point. We will look at all that. And the model, we can also include a variable called net rate, and then we look at, and Vensim will also update this rate level graph. So, I am going to go to Vensim now, I am going to file, save as, and just change it. So, that I need to include the deaths, added a flow death rate, and I have another variable called as fractional death rate, arrow connecting population to death rate, fractional death rate to death rate, click equation, fractional death rate we wanted 0.07, 1 over month is the fractional death rate is 0.07, death is days per month, nothing but population times fractional death rate. So, death rate is product of these two, fractional death rate is 0.07, a constant. In population P, once you click it, you will find the death rate is also included here. So leave it. And initial value we had 2000, just change it to 2. Change initial value of population back to 2. Let's click OK. Let's click the play button. Click population. Click the causes strip. Now you get interesting graph. The population of stock continues to exhibit a S-shaped pattern. You see in here. So the S-shaped growth is always with reference to the stock value. Okay. Death rate is just a constant in proportion to the population. So it also has to exhibit the same shape. Just a constant times death rate. But if you look at net birth rate, in the previous time when you observed, it increased to a peak and then fell down and hit 0. But here now net birth rate went up, then as it is coming down, it intersected with the death rate and then both became equal at around 40, 46, and then both are now constant values. To see the actual net rate falling to 0, we need to actually model the net rate. Right. So, to model the net rate, we can just introduce a new variable called as net rate, connect your birth rate and death rate to this net rate, click equation, click net rate, click births minus deaths, births minus deaths, so it's a net rate. Let us again simulate. Now if we plot net rate, you will find that the net rate will fall to 0, as you see here, and the value of net rate. So to visualize all the values, select all 4, click the tables, you get a table of values, keep scrolling. The net rate here peaks at about around time 50. Where is net rate here? Around the same value of 49.99. It's around time 56. Quite close to when the population value P is near 500. So, but death rate and net birth rate are still different. But as that, yeah. So this is the net rate. Net rate peaks. The net rate peaks at actually 20 at time 47. If you observe, the net rate is the third column for me. It's a 21.1134 value. Very small to read, but you can see it from in your computer. It's around 47. Just observe that the net birth rate actually peaks much later at time 52 or 53. At around 56 is when birth rate peaks, but net rate had peaked much earlier at around time 47 itself. So it can be different. And then death rate and birth rate both will converge to in this case around 45.5. The population peaks at around 650 or something. When it peaks is about around time 80. The inflection point is somewhere around 44, 45, which coincides with the peak 47, which coincides with the peak of the net rate, not the birth rate or the death rate. At the peak of the net rate is the inflection point. Yeah. You can try this. It include the next rate, 2 rates also in the graph, and see whether we are getting the graph very similar to what we have plotted. Straight line and the curve, intersection, everything can be visualized. Let's try expand on this. Suppose other limiting factors such as starvation affects death rate non-linearly. Birth rate we affected, let us assume it also affects death rate. What will be expected behavior of system? Plot the expected rate level graph. How can we expect fractional rate to change with population capacity ratio? So, for that, so suppose death rate is also changing non-linearly, what will happen? That is the question. Let us understand it here. So, if death rate also changes non-linearly, just let us look at this graph. Even if it changes non-linearly, this shape is going to remain the same. Perhaps it may, the point of saturation may be lower, right. So, what does it mean by changing death rate non-linearly? That means death rate is going to increase as I come closer to, as the level becomes larger and larger, as level goes closer to carrying capacity, my death rate is going to increase, right. Suppose the death rate increases like this, meaning death rate is changing non-linearly now. Okay. So, now birth rate we already the same graph. Now, you can see the point of intersection is here, and my new net rate graph comes like this. So, this becomes a new net rate graph. So, what you are observing is as death also changes non-linearly, my equilibrium point shifts leftwards, or equilibrium point becomes lower, or the level at which I expect to saturate becomes lower. So, if we did not have the death rate at all as a constraint, the first case the birth rate increased, then it fell down and hit level, that is the maximum I can reach. If I have death rate linearly increasing, then my birth rate graph is going to intersect at much early point, that means equilibrium point is shifts lower, and if death is also increasing non-linearly, then my equilibrium point will be even lower. This will be the new equilibrium point, it will be somewhere here. So, you can expect the similar behavior, and equilibrium point is lower. We can also model this, we will continue it in next class.